Okay, so as it was announced, I will talk about CSPs and some compactness principles. So as you will see, these are two different but kind of similar topics or kind of questions, and then I will talk about some non-trivial relations between the two. I should also say that the first topic, the CSPs, CSP is the abbreviation of constraint satisfaction problem, right? So that's like the big research topic. So that's been heavily researched in the last few decades, and also that's where I'm coming from. And the other one is like more recent, so there's some open questions and future research problem that you can think about. Nevertheless, I will start with compactness, right? So there is this theorem named after Erdős and De Bruijn, which is saying that every graph which is finitely three-colorable, meaning that all finite subgraphs are three-colorable, the graph itself is also three-colorable. Right? So this is one theorem, and if you ever taken a course in model theory and logic, you should know that it actually follows from the compactness theorem, actually already for propositional logic. Right? So this heavily uses the axiom of choice, if you know the proof. Actually, not quite, right? It turns out the ultrafilter principle, the ultrafilter lemma, is already enough to prove this, right? So the ultrafilter principle is saying that every filter on your set can be extended to an ultrafilter. And this is known to be strictly weaker than the axiom of choice, but it's still quite strong. Right, and a few decades later, actually it was proved by Lochley that you can reverse this. So over ZF, this Erdős, De Bruijn, and the ultrafilter principle are equivalent. Okay, now in comparison, there is this baby version of this, which is just changing everything to two-colorability, right? And if you think about it, it's like obviously the same proof works. You can just use compactness, but for this, actually, this is not even required. You can almost prove this without any choice, right? Because if a graph is finitely two-colorable, it means that there is no odd cycles in it. So the usual way that you would find two colorings, you can pick your favorite vertex, color it red, all the neighbors blue, and so on. You always have one choice, right? So you can just continue. So this is like almost choiceless, not quite, because you have to do this separately for each of the components. So you need the axiom of choice for two-element sets, right? So this is like a very weak version of the axiom of choice. Sometimes I tell this example that this is basically where there's like an infinite set of people, each given a pair of socks, and then we want to make them to put on their socks, right? And you have to make a choice which one to put on their left feet, right? So this is what it is. Yes, and now if you're coming from computer science, you can think about this analogy is that three-coloring, or finding three-coloring, or even deciding that something is three-colorable is hard, whereas two-coloring is easy, right? And then basically I want to generalize this observation. Okay, now I'm going a bit more formal. So these two and three colorings, these are homomorphism problems, so it can be thought of as homomorphism problems. And then actually, I'm not even talking about graphs, so I can imagine any finite relational structure. Actually, it doesn't matter, you can think of graphs or whatever, right? Finiteness is actually also not really needed for the definitions, but I also assume this in this talk. Okay, so first of all, there is this compactness principle for this structure B. So I denote it by K sub B. And it says that for every structure A, and it's secretly assumed that it has the same signature as B, if all finite substructures of A homomorphically maps to B, then the whole structure A does as well. Right? So this is a statement, could be true or false in universe. And then, okay, this is where CSPs come into the picture. So CSP over a structure is a decision problem, right? So it's like a computational problem, and it's phrased in terms of homomorphisms. So we have input structure, say A. Again, we assume it has the same signature as B. And the question is whether there's a homomorphism from A to B. And in general, we are interested in the computation and complexity of this. Right, and basically, this is how I phrase this, maybe it's sort of like a generalization of this observation that I made earlier, that is it true that for harder CSPs, so harder CSPs correspond to stronger compactness principle over ZF? Okay, so the answer to this is kind of yes, in a sense that, and basically this is what I will talk about in the next few minutes, that in what sense this is true. And in order to do this, I need to introduce some kind of technical notions, but it's not super complicated. And this is actually coming from like the theory of CSPs that was mostly invented for this purpose exactly. So I will talk about PP powers and PP constructions. So I will start with PP powers. That's the slightly more technical one. So I'm saying that the structure B is a PP power of the structure A if first of all B lives on a power set of A, right? So that's fine. And all relations which live on B, they're PP definable in A, so it's like they're becoming a big relation. And what is PP definitions? The PP stands for primitive positive. And it means it could be any formula with this restriction. It's quite restricted. You can only use existential quantifiers and conjunctions of atomic formulas inside. So yeah, so this is primitive positive. And there is this observation that there is a reduction from the PP power, the CSP over the PP power structure to the CSP over the original structure, and it's a log space reduction. And the reason for this, maybe I say a few words, but basically what happens is that there's also like a logical formulation of CSPs. So if you write down what a homomorphism is, then you're getting PP formulas or PP sentences, right? And this is like nesting, so like you're plugging in PP definable relations in a PP formula. So like if you make the calculation, it's just getting a bigger PP formula. So this is quite straightforward if you think about it for a few minutes. By a recent result, it's actually this one is not super deep, but it's like there's some technical issues that you have to deal with. So this is due to these three Hungarian authors, Katai, Tóth, and Vignyánszky. It says that if B is PP power of A, then we have this implication between the compactness principle, right? So this is going forward, whereas the previous one is going backwards. Right. Now, PP constructions, so we need to add another notion to make this a bit more robust. So we need to add homomorphic equivalence. Turns out this is enough. So I'm saying the two structures are homomorphically equivalent if there are homomorphisms between them in both directions. Okay, and what happens if this is the case? It's two observations. First of all, they just have the same CSP, right? We can just compose homomorphisms. And also the compactness principles are the same. I mean, it's just literally the same statement. Okay, and PP construction means that we combine the two things. So structure PP constructs another one if it's homomorphically equivalent to a PP power of the structure. And it turns out that you can compose this for non-trivial reasons, but you can do this. And here I put this as a corollary that even for PP constructions, we have this log space reduction and this implication between the compactness principles for the exact same reason. Okay, now when it comes to finite structures, at least from the point of view of CSPs, there are two types of structures in the world. So, and one type, so one of those are called omni-expressive. So those are the ones which PP construct all finite structures. So K3 is one of them, as it turns out. So actually, for this reason, it's enough to PP construct just K3, but there are many other examples. So for instance, all clicks, and there's also this Boolean ternary not all equal relation, which basically corresponds to hypergraph colorings. And yeah. And basically, from what I said, it already follows that if a structure is omni-expressive, then the CSP is hard, because tree coloring is hard, right? And we also know that if the structure is omni-expressive, then the corresponding compactness principle is as strong as it gets, right? Equivalent to the ultrafilter principle. That's the strongest you can get. Okay, and so what happens with the other structures? So I put here two dichotomies. So this is the very famous one. This is the finite CSP dichotomy. It's a quite that's the end of a really long story. It's been a conjecture for quite a while, and it's a quite deep theory needed to prove this. So this is due to Bulatov and Shuk, which is saying that if the structure is not omniexpressive, then its CSP is in P. Right? So it's dichotomy because we have two cases, right? So we have this, and it's P. In the other cases, it's NP complete. There is no intermediate cases. Right, and what is the dichotomy? So again, it's the same three Hungarian guys proved. Basically, this is the dichotomy we have for compactness. So they constructed a single model of ZF where the compactness principle over the structure holds if and only if the structure is not omniexpressive. Right, so because of this reason, the ultrafilter principle fails, but all the other ones, which are not automatically equivalent, they actually hold. Right, so we have this separation. Okay, now I will check the time. Oh, okay, I need to speed up a bit. Okay, now in the last few minutes, I want to talk about the direction that I also got interested in, and that's the promise version of these problems. So as for CSPs, this has been introduced I don't know, at least 10 years ago or something, so this is a quite natural direction of research. So in this setting, we have this promise template that consists of two structures, and we just assume that there's homomorphism to the first one to the second one. So from this red to the green one. And the promise CSP is very similar to the regular vanilla CSP. The only difference is that we have two structures, right, to find homomorphisms to. And we want to say yes if there's a homomorphism to the first one, and we want to say no if there is no homomorphism to the second one. Right? And there's some other cases, then we don't care what we say, or you can say that someone promises you, hence the name, that either of the two cases happens. Right? So this is distinguishing 3 colorable graphs from not even 1 million colorable graphs. How hard is it to do that? Okay, and the promise compactness, I think it's also quite natural. As far as I know, it's my definition, but I think it's quite straightforward. So basically the same statement. It starts off the same for every structure A. If all finite substructures homomorphically map to B, then the whole structure homomorphically map to C, right? So you can consider these statements. Right. Okay, and then, maybe I should quickly say that all these PP construction, machinery, and some other things we didn't talk about, they just straight up generalize in this promise setting. And it turns out that the K3, K4 template is omniexpressive in the same sense. And it has the usual consequences. So first of all, distinguishing 3 colorable graphs and not 4 colorable graphs is NP complete. We know this, maybe not a big surprise. But we also have this conclusion for compactness principles, which I think it's quite fun. Right? So this is basically saying that if we happen to live in a universe where every graph, which is finitely 3 colorable, is 4 colorable, then actually all those graphs can be colored by 3 colors. So somehow, by some magic, we can just remove 1 color. Which I find this quite fun. And then obviously you want to push this result. Turns out if you increase this number 4 to 5, for instance, then things are not so nice. So we know that K3, K5 is not omniexpressive, but for different reasons, we know that the corresponding PCSP is still NP complete. And my little contribution here is that I think you can guess it's the same conclusion as here, but you can change the number 4 to 5, still equivalent. So I can remove, I was able to remove the second color with quite a bit of effort. So somehow this is still true, but we have to work quite a bit. And maybe I should also say that two proofs are they don't rely on each other, but there's a big overlap. There's some machinery that both of them are using, but it's So you'll have to do some new things. And I would expect the audience to ask what happens for K3, K6, and the short answer is that we don't know anything for those templates. So neither in terms of the complexity of the promised CSP, nor in terms of the strength of the compactness principle. And yeah, and the obvious conjecture is that it's still equivalent, or it's still hard in the case of PCSPs. Okay, actually I have one more slide, but I can also end here. I think I will do, because, Okay, then 2 more minutes. So, so actually it's the same result. Okay, it's a bit more difficult to read, but it turns out that everything becomes much nicer for hypergraphs colorings, right? So as I mentioned this, that these are the templates, right? So distinguishing 2 colorable 3 uniform hypergraphs from not even C colorable ones is still hard for any C greater than or equal to 2. It's a big secret. It's actually the same result as the previous one. So, but anyways, and also knife proofs works for this, right? So we still have this equivalence. And I also spell this out. This is a slightly stronger version. I think it's quite nice. It says that imagine that we live in a universe where every finitely 2 color or 3 uniform hypergraph can be colored by finitely many colors. Then actually it turns out that in all these universes, all these hypergraphs can be colored by 2 colors. So I can remove infinitely many colors. Well, it's always finitely many, but any number.